Hello everyone, we are team IITGnGPT and we are presenting the paper LLM-DetectAIve. Most prior work before this paper focused on binary classification problem, detecting whether a text is human written or machine generated. But this approach is too narrow and it's not sufficient. Some of the current methods what people do is generally write some email or any text content by themselves and then ask an AI model, for example ChatGPT or Claude, to enhance it or adjust its tone, make it more professional or various other things. So this type of text is a new category which this paper has introduced, which is human written and machine humanized. Another growing trend, another strategy what people are using is first get an initial response from an LLM after an initial prompt, and then again send it to another LLM, maybe the same LLM or even a different LLM, and then asking it to again tweak it, for example, make it more professional, longer, shorter, change the style of writing, and other things like that. This is called machine generated and machine humanized. So first, the motivation for the authors of the paper. The authors felt that simply identifying text as human written or machine generated wasn't enough. A more fine-grained classification was needed. A key point from the paper was that in education, even modifying human written text using LLMs is often prohibited. So with just the binary classification, we cannot fairly evaluate students' genuine abilities and knowledge. The motivation for us to choose this project was like when we went through the list of projects, this one immediately caught our attention because this is something which we have personally faced in the last 2 years at college. We were curious about how these AI text checkers actually work, like when we see these percentages, how exactly they're calculating it, and how this paper moved from a 2-class problem to a 4-class problem also fascinated us. And we thought that, okay, now they've made it into a 4-class problem, what more can we do it? Like, can we add percentages to even the 4-class, like how much machine humanized it is and how much human written is it? So there were a lot of ways to explore this problem. And this was quite open-ended scenario and we thought to work with this.
Recently, a lot of work has gone into detecting AI-generated text. For example, DetectGPT proposed a zero-shot method that uses probability curvature of language models for binary detection between human and AI. But this struggles with mixed texts, which are partly human, partly AI written. Then M4GT Bench is a large multilingual benchmark which spans multiple domains and generators. It evaluates detection, source attribution, and mixed text. But this was only a benchmark and not a new method of detecting AI or human text. Then in the SEM Eval 2024 workshop, there was a task with standardized evaluation for tasks like classification, source model identification, and boundary detection. Again, this was only for binary detection and not for nuanced categories like partly human, partly AI. For that, there was a dataset called Mixset, which was a dataset of human AI co-authored texts. But this was only limited in scale and not very systematic. So this system was tested with many popular detectors like GPT-0, GPT, and Sapling AI. But all of them did not cover 4-class detection. GPT-0 covered a mixed text class, but it was only limited to very few reruns per day. So the comparison on the full dataset was not possible. For this, they only sampled a subset of the dataset and then tested the models. Out of this, LLM-DetectAIve got the highest accuracy. So the contribution of this paper is a 4-way classification system as mentioned, and for this they created a new dataset, which was multi-domain, multi-generated, and systematically edited. More importantly, they focused on robustness with adversarial training with DNNs. They also have a publicly available demo and code for everyone to use.
Let me begin with the core issue, distribution shift. When we train a detector on one domain, the model learns stylistic and lexical cues specific to that domain. Within the same domain, performance is excellent, but the moment we test on a different domain, accuracy drops drastically. This happens because instead of capturing general indicators of machine versus human writing, the model overfits to the domain-specific artifacts. If we see at the figure here, it shows that in-domain and out-of-domain performances of Roberta. Along the diagonal, we can see where training and testing are done on the same domain. Accuracy is very high, but off diagonal, when we switch domains, accuracy drops sharply. To address this problem, the paper explores 3 strategies: domain-specific detectors, where we train a separate model for each domain; universal detector, where one model is trained across multiple domains with balanced dataset; and domain adversarial neural networks (DNNs), where we use adversarial training to encourage the model to learn domain invariant features. Let's start with the first strategy, domain-specific detectors. Here, Roberta and Distilbert were fine-tuned separately on datasets like ARC7 and Outfox. Research showed that Roberta consistently outperformed Distilbert, reaching about 95% accuracy on both domains. Distilbert, being smaller and faster, performed slightly worse, but still fairly competitive. However, this approach requires manual domain selection, which is impractical. Another issue is scalability, which means for every new domain, we need to fine-tune a separate model. It increases cost and makes deployment impractical. To reduce this extra effort, we developed the second strategy, universal detectors. Here, instead of splitting by domain, we merged 6 sources, Aeshaa, Wikipedia, WikiHow, Reddit, PeerRead, and Outfox into a single balanced training set. Looking at the dataset distribution table, we can see how the classes were balanced across domains. In this setup, Roberta and DeBerta were trained. We can see that DeBerta performed best with about 95.7% accuracy, slightly ahead of Roberta. The benefit of this method is that user does not need to specify the domain in advance. But the drawback is that when tested on entirely unseen domains, performance still drops. This is what motivates us with the third strategy, domain adversarial neural networks.
So the next strategy is the DANN, Domain Adversarial Neural Network. The DANN was proposed by Gannon in 2016. The DANN contains 3 components: the representation extractor. The representation extractor extracts the feature from the input words, and then the label predictor identifies which class it belongs to. For example, human written, machine generated, etc. Then there is a domain classifier, which identifies which domain the text has been taken from. Then using the domain classifier, we find the domain loss, and using a gradient reversal method, we will negate the loss of the domain classifier. So the model will get more confused on which domain the text has been taken from. The advantage of doing this is that we'll get a higher label accuracy while having a lower domain accuracy. So the model does not attach to the sentiments of each domain. Now, while using the DAN on top of Roberta, it enhances the overall performance compared to the fine-tuned Roberta. So this is a mixed set detection. It was proposed by Zhang. It is the ability of an LLM to identify both a mixed category of human written and mixed category of machine generated text. So in our day-to-day lives, what happens is we might ask a model to write something, and then the students will take and humanize it in such a way that it is not detectable by the DetectAIve. So this is a problem that was also mentioned in the paper. So when what happens was, when it was tested on the mix set, the accuracy was dropped from 96 to 97% to about 60 to 66%. For this, the paper suggests taking ILTS, training the model on ILTS and mix it. So the next is the web application that was hosted on Hugging Face. So they have 2 types of application. One is an automatic text detection and one is a human detector playground. So in the automatic text detection, we have to input a text of 50 to 500 words, and when the check origin button is clicked, it will check which of the 4 classes the text belongs to. And then there is also the human playground, where we can copy a text, and then we can check, we can select which label it might belong to, and then it will tell if it is a correct statement or an incorrect statement.
Now let's discuss the limitations of the current system. So the first limitation is that the system misses out on the class of AI written plus human edited texts. These are a common real world scenario, but the system fails to detect this, which reduces its practicality. The second limitation is the formatting bias. So some domains like PeerRead or WikiHow, they have very specific formatting styles, like let's say bullet points or headers. The model, instead of focusing on things it should focus on, like the words used in a text or the sentence structure or the grammar, it focuses on formatting, which has led to a bias in how the model classifies the texts. Third, the model is trained only on English datasets currently, and as we know that there are a lot of languages out there in which AI generated text can be present. So this system fails to address this problem of detecting in other languages or in multilingual texts. Now, this is the future work proposed by the authors to address these limitations and also to make the model more robust. First, they propose the use of DANNs to generators.
So the current system has applied DANS to domains, which has helped the model generalize to some extent on the different domains that are used. We can also use DANS on AI text generators like let's say GPT or Claude or Gemini, so that the model can recognize any text from any general AI generator and possibly even an unknown generator. Next, they propose adding the new category of machine written plus human edited texts. So, how this can be done is that we can collect some data of text first generated by machine and then edited by a human, then train the model on this new data along with the old data, and then add a fifth category of machine written, human edited. However, the data collection part is very time taking. Next, they propose multilingual expansion. So we can collect in some data in other languages in which datasets are widely available, like let's say Spanish or Chinese or French or even Indian languages like Hindi, and then we can train a multilingual model like MBERT or XLMR. Lastly, they propose bias reduction due to the formatting. We can implement this by pre-processing all textual data to either remove all the formatting or to use a consistent formatting style across all domains so that the model can focus on relevant things like the writing style rather than irrelevant things like the formatting.
Novelty from the existing work. First, we have decided that we'll show a percent score of how much human-generated content and machine-generated content is there for each of the categories, so that the person has an idea of how much they have to reduce. Then we'll also pinpoint the areas where the text is showing as machine-generated or machine-polished. And the other main thing that we're trying to achieve is to show that which AI is the source of the text. For example, Claude, ChatGPT, Gemini, etc. And this would need more AI-specific data, and we'll try to find datasets for this, or we can make them by ourselves. And the last that we are thinking that we can achieve later is to enable the development of a robust multilingual detection model so that we can use other languages as the dataset and use them too.
About the experimental plan, which is non-incremental. So this is a new model that we can use. So first we'll get the word vector. So we can from the text we can extract the vector embedding from it. Uh, and then basically we can pass it through Deberta v3. So we are using Deberta v3 because it will have a larger context length. So I think that is better than the Deberta v1, which is 512. And then this is basically a multitask learning. So the y1 basically denotes the loss for the four-way classification, and y2 denotes the like the logic for the three-way classification. The four ways for the four classes. So human generated, machine generated, machine generated, machine edited, human generated, and machine polished. So the four classes, and the other is for the LLM use. So we can learn it together, and we can also add some. So this is a loss, and this is basically the cross entropy loss because it's a classification problem. And here, what we can do is, let's say, add some alpha value to weigh the losses in a different way. But like for simplicity, L1 plus L2. So this is a multitask learning, and so it allows for shared learning. So it is better in the sense that it is not weighing only one factor over other. So that's why we can even add a weight like lambda factor or something. But yeah, for now the lambda is one, for example. And yeah, so this is a multi task learning. And so for the data set, so M4GT already has the binary detection and the multi-way model. So which is the model needed. So what we can do is first add on to this the machine polished, machine edited. So we'll just use the machine generated text and based on some prompts, like pass these texts through the prompts and generates a few more data entities for machine generated, machine polished, and also human generated, machine polished. So based on this, we can build it using various LLMs. And for each of the data rows, we can have a tag for like basically which model has generated it, like let's say GPT, Llama, or Gemini. So yeah, so we can use that, and yeah, so yep, with various LLM, yeah, and these are the references.